Aloha class. We get into some parametrics and some polars now. It's pretty cool stuff. There's stuff that's been in our calculators forever. You've probably wondered why it's been there. We get to look at that stuff today. And also, Holmes wants to say aloha, right? It's probably about a Christmas break right now. And guess what? Get ready to get crazy. I've got Papa Holmes, a.k.a. Buddy. Thanks to my classmates that got that for me. I appreciate it. Got it from Mr. Jasper, Garbeck, Downing, Smerica. I hope I didn't miss anybody. If I did, let me know. I will give you a shout out on one of my future videos. What's up? We're back together. What's up? Give some love. All right. Here we go. Intro to parametrics and vector calculus. All right. This gets to be some fun stuff because we get to finally do some different stuff. Okay. It says without a calculator, make a table, sketch a curve, indicating the direction of your graph, then eliminate the parameter. Right. What the heck does all that stuff mean? Well, here we go. Let's go ahead and draw this guy. Oh my gosh, this is crazy. It's brand new. Look at all that stuff. I like that red. Is that going to give me some red? Sweet. It's a little bit thicker than I would like. So maybe I have to change some settings, but we'll go ahead and get after it and see if we're okay. All right. So how do I make a table if I want to graph a parametric? Okay. All right, class, I'm going to have to try with this big thing. I tried to change it. I didn't think I was able to. Okay, so what we need for this is we need a T column, we need an X column, and we need a Y column, okay? And then it says we're going to do this from a time of -2 to 3. So let's go ahead and plug in a -2. Now, I did this earlier, so I'm going to save myself some time. And if I plug that -2 in for the T's, I get an X of 0 and a Y of -1. So we're actually going to start graphing this bad boy. Where would this particle be at time -2? It'd be at 0, -1. So it's right there. It's getting started, okay? Let's see what happens as we travel to -1. And if I put a -1 in there, I get a -3 and a -1/2. So that would be a 1, 2 tree. And a -1/2 would be about there. Now, guess what? These are parametrics. And parametrics show us the direction of the path, which is pretty cool. We put a 0 in that bad boy. I get a -4, 0. Kind of comes back there. Ooh, it's kind of interesting. It traveled for 1 second, but it looks like it's slowing down a little bit. That's a little kind of cool going on right there, huh, class? We put a 1 in there. I get a -3 and a 1/2. You can check my math. That would be a 1 right there, so it'd be there. Ooh, it's turned. Snap. This bad boy wants to come back. Okay, plug a 2 in there. If I put a 2 in there, I get a 0, 1. So I put that, boom, it comes back. Ooh, look at that. Just sped up a little bit. And then we go to 3. If I plug a 3 in there, what do we get? 5, 3/2. Okay, so 3/2 would be between 1 and 2. 1, 2, 3, 4, and 5. So it'd be about there. And then it goes, wow, it kind of speeds up super duper. How about that? That's pretty cool. So what it does, and if you noticed, I don't know about you, but that kind of looks like a sidewards parabola. And one of the things that they ask us to do in this problem is they ask us to eliminate the parameter. So let's see what that would look like, huh? And the way we eliminate a parameter is we want to put this in terms of just X's and Y's. So one thing looks doable. That looks like I could solve it for T. And when I solve that guy for T, I could just go ahead and plug that into my X equation. And believe it or not, that's going to give me an equation in terms of X's and Y's. And that would be eliminating the parameter because I was able to eliminate the T. How about that? That marker's not too bad. It's a little big. I think it will get to be a problem in some tougher problems, but not bad, huh? And there we go. We eliminated the parabola. How about that? That would be a parabola that would open up to the right, class? And if you look, it has a transformation shifted 4 units to the left. Interesting, huh? Pretty cool stuff if you ask me. Oh, I forgot I wanted to show you this cool stuff. Go ahead and get out those calculators. Okay, and I want to show you something really cool. Oh no, they changed the screen on me. How about it? Okay, so let's get out our calculators. And what I want you to do is I want you to go to mode. And the really cool thing about going to mode here is that you notice that in that 1, 2, 3, 5th line, we have function parametric. So I want you to go down here, and I want you to change to parametric because now we're going to be graphing parametrics. Now, if you change it to parametric and then you go to your y equals, look at this. Spling, spling, spling. Oh, cool. I get a little x1 and a y1, right? And then we want it in terms of t. So let's go ahead and plug in those those functions, those parametric functions, right? We have an x component, we have a y component. Okay, and then what we have to do is we always want to adjust the windows here when we go. Okay, we kind of know by the table of values that we had that my t goes from -2 to 3. If I look at my x values and what goes from kind of -4 to 5, so I'm going to go in my x, I'm just going to go -10 to 10. Remember, I like doing the 0 scale so you don't see those little tick marks. And then the y mins, it kind of really just goes from -1 to 1.5. So I'm just going to go -2 to 2. And guess what? Plug in all that stuff. I'll give you a moment. Actually, hit pause. Okay, hit pause. When you're done plugging that in, unpause it. All right, and then if I hit graph, look at that. And it's so cool. It shows me the path. Now, I already had it graphed, but what I'm going to show you is some cool things that we can do here. Let's go back to window here. And if I go down to t-step, okay, check this out. That's how fast it graphs it. It's 0.13 step. That means it's just graphing every 0.13. Let's go to like, let's try 0.05. Okay, and let's hit graph again. Let's see what happens. Oh, what? That just blew. Papa Homie says we couldn't do that back in the day. Homie Home says we can now. Papa, aka buddy. All right. So, and it's cool, and you can play with that. And the cool thing about parametrics is they give us the path, the direction, and the speed, which is really super cool if you were to ask me. All right, let's get back here to our notes. Okay, let's put this up a little bit. You can probably fill in some notes, right, if you were paying attention. So let's go ahead and fill those in. What do you notice about okay, while rectangular equations on restricted intervals show the path. Ooh, tell me it works. Okay, good. The path. Parametric equations show the path. What else did they show us? They showed us the direction. And what else did they show us? They actually show us the speed. And remember, you can slow down those steps to really see how fast it's going. All right, we're going to keep on moving. I got a little bit of a cough. Sorry. All right, example 2, part of your homework. Do it on your own. Okay, we're going to do example 3 together. All right, let's change this up. Let's go a little light blue. That's kind of cool. All right, so we're going to do a little table. T, an X, and a Y. Okay, now, oh snap, it's trig functions. They don't give me a domain to kind of work it on, but we all know trig functions. Hey, let's just do what we're familiar with. Let's just start with 0, right? We want it to be easy math. If I plug a 0 in for t, cosine of 0 is 1, 2 plus 3 is 5. If I put a 0 in for the sine of 0 is 0, so it's just -1. Let's go ahead and graph that bad boy. So 5, 1, 2, 3, 4, 5, -1. Okay, that's where this particular parametric is starting out, this particle. Okay, now there's a lot of values I could pick between 0 and pi over 2. I'm going to try to get away with it because if I pick those other values, I'm going to have radicals and that'd be tough to graph and all that stuff. So I'm going to try pi over 2 and see if it gives me enough to get an idea of what this graph looks like. All right, so we're going to plug a pi over 2. Cosine of pi over 2 is 0, so it's just going to be 2. Sine of pi over 2 is 1, and -1 plus 2 is 1. So it will be 2 comma 1 would be right there. Dang, I almost graphed that wrong. So there is my direction of my particle, right? And I'm moving in that direction. Pretty quick speed. Okay, but that worked out, right? I could pick like pi over 3. I could pick pi over 4, pi over 6. But that was enough to get an idea of what the graph looked like. I'm going to actually change a color here. I'm going to make it a little bit, purple. I love purple. Okay, so we go from there to there, and that is my direction. All right, now let's go ahead and choose pi. That'd be my next guy. Plug a pi in there. I get a -1. That'd be a -3, so that'd be 2 plus a -3, which would be a -1. Plug a pi in there. That'd be 0, so it's just, how about that? -1, comma, -1. -1, comma, -1. Ooh, it's coming back around here, right? And it'd be curved, and I can pick some more values if I wanted to see it, how it was curved. Next value, let's pick 3 pi over 2. And hopefully you're noticing a little bit of a pattern. Plug 3 pi over 2 over there. Cosine of 3 pi over 2 is 0. So I get a little 2 right there. 3 pi over 2 is actually -1. So that'd be a -2. A -1 and a -2 gives me a -3. So we're at 2 comma -3. How about that? Oh my gosh, this looks great. That looks like a circle, right? And then if I plug a little 2 pi in there, it gets me back to the beginning, 5 comma -1. There you go. And remember, you could always pick more values if you wanted to see, but that looks like a circle. Huh, that is a circle for sure. Real, what? All right, now how do I eliminate that parameter, right? I'm dealing with sines and I'm dealing with cosines. One way I could eliminate that parameter is let's go ahead and get cosine of t by itself, and let's just see what that gives us. If I get cosine of t by itself, I'm going to subtract that 2 and divide by the 3. Okay, there we go. Now let's get that sine t by itself. Now why am I doing this? You're going to see here in a moment, right? Just got to use all those tools in my toolbox. I'm going to add that 1 over, so I get 1 plus 1, y plus 1 over 2. All right, now how could I use the tools in my toolbox? Well, there's one Pythagorean identity we should always be familiar with, right? And that would be that sine squared, right? If I square my sine and I square my cosine, what do I get, class? I get 1, right? And that's an equation, and that's what we're trying to do. And believe it or not, I can eliminate the parameter this way. How? Direct sub, plug and chug, right? So I'm going to put a x minus 2 up. Well, here, I'm not going to erase that. Okay, that's my sine. Oh, that's my cosine, right? And I'm going to square it, and then my sine's going to come over here. So that's the way it was written up there. So I kind of kept it consistent, and that's still equal to 1. And believe it or not, I could simplify this to be x minus 2 squared over 4 plus y plus 1 squared over, whoops, I messed something up. What was it? Oh, that should be 3, and so that should be a 9er. And that would be 4 equals 1. And you know what's cool is hopefully you got that tool in those 2 boxes. That is a Papa Holmes ellipse. Good job, Pops. That's an ellipse. It's an ellipse that has a center of 2 comma -1. It sure does. And remember, if this 9 is on the bottom, the square root of 9 is 3. It means you go 3 units this way. It means you go 3 units this way. That 4, square root of 4 is 2. It means you go 2 units up. You go 2 units down, thus giving you an ellipse. But the cool thing about parametrics is it gives us direction, it gives us its path, and it gives us its speed. Remember, rectangular coordinates simply give us direction, right? And then we just eliminate the parameter. All right. Cool. Let's keep rolling. All right. BTOC. BT, right? We got to do a dance for that. BOTC, right? Something like that. What? BOTC. Somebody help me out. Come to school with a cool little dance with that. Give you maybe some bonus or some bonus jumpers in class. All right, I'm so sorry. Look at the new thing doesn't give me the time, so I got to keep rolling. If not, this video might get too long. All right, here we go. Bring on the calculators. Let's go back here to some red. All right, now first derivative of parametrics, kind of cool. dy dx is just simply dy dt over dx dt. Obviously, dx dt cannot be 0. Second derivative a little bit different. Okay, something you definitely want to make sure you have memorized. Okay, and the second derivative, okay, is simply, and we're just going to go straight to this bad boy. Okay, if you want to know how all this works, come on in, please. It's kind of cool actually how it does. But the second derivative is you're going to take the derivative. You're going to take the derivative. Oh, sweet, awesome. You're going to take the derivative of dy dx, and you're going to divide that by dx dt. How does that work out? You're about to see in a moment. And here is this moment. All right. Okay, so without a calculator, okay, find dy dx and find the second derivative. Okay, so dy dx, and this is for parametrics. Kind of cool thing is we still keep it consistent as that. But the way we do it with parametrics is simply dy dt divided by dx dt. That's it. Okay, so what the heck is that? Well, dy dt, derivative of that bad boy, is simply 6t minus 2. Right, class? Derivative of that bad boy would be, okay, that'd be 2t to the 1/2, right? Drop that 1/2, and I just get t to the negative 1/2. Okay, let's simplify that before we go ahead and evaluate it for t equal to 1. And if I simplify that would be 6t, that'd be t to the first, and 1 minus negative 1/2 would be 3/2. Right, class? And then my other one would be minus 2t to the positive 1/2, okay? And then they ask me to do dy dx when t is equal to 1. So we're going to plug a 1 in for that. I get a 6 minus 2, which is 4. Okay? That's the first derivative. That's it, right? We've been doing that all year. Not bad, right? Parametrics, okay? Here we go. Second derivative. This is where it can get a little bit tricky, and you need to know the formula, okay? The second derivative, if I'm dealing with parametrics, okay, it's a formula you kind of want to know. All right, you're going to take the derivative with respect to t of dy dx, okay? And you're going to divide that by dx dt. That's all you got to know, okay? So what the heck does that mean? Well, you're going to take the derivative with respect to t of the first derivative. The first derivative was 6t to the 3/2 minus 2 to the 1/2, right? And I'm going to divide that by the derivative of dx dt. The derivative of dx dt, remember, was just t to the, drop that, subtract to the negative 1/2. All right, so let's go ahead and take the derivative of the numerator with respect to t, which would be 18 over 2, which would be 9t, subtract 1 to the 1/2. And then I'm going to bring that 1/2 down, and I'm going to get a, ooh, I forgot a little t there, didn't I? A t to the negative 1/2. Ooh, negative 1/2. All over t to the negative 1/2. Let's simplify that bad boy. And I would get 9t. Okay, that'd be 1/2 minus negative 1/2 to the first, and then minus 1. How about that? That's the second derivative. Not bad, right, class? Just a formula you have to remember, and make sure you practice. Make sure you do your homework, okay? So let's go ahead and evaluate this. This is where my big marker kind of is going to help me struggle a little bit. So sorry that I'm going over here, but I'm going to evaluate that at t equals 1, which would be 9 minus 1, which would be 8. 1, 2, 3, 4, 5, 6, 8, 7, 8. 8 is 8 in Japanese. Oh my gosh, I thought I paused it. Okay, let's keep on bringing on some calculators. Okay, this one says without a calculator, write the equation of a tangent line. Well, how do we write the equation of a tangent line? Y minus y1 equals m times the quantity x minus x1. Not bad, huh, class? Especially because I can find what x1 is. X1 is equal to 4 cosine of 3 pi over 4. 3 pi over 4 is cosine, that's the second quadrant, right? So that'd be negative radical 2 over 2, which would be negative 2 radical 2. And then my y1 would be equal to 3 sine of 3 pi over 4, which would be radical 2 over 2. Positive though, right, class? Make sure you're very careful with your positives and your negatives, okay? So that's my y1, that's my x1. So remember, going back to like the first month of AP Calc, this is exactly what we did. Equals mx plus 2 radical 2. So now all I have to do is find m. How do I find m? dy dx, right, class? Evaluated at 3 pi over 4. I'll do that later because this is for parametrics, which means I'm going to do dy dt over dx dt. dy dt is equal to 3 sine t. Derivative of that would be 3 cosine of t. The derivative of 4 cosine t would be negative 4 sine of t. Right, I'm going to go ahead and evaluate this bad boy. Dx at t equals 3 pi over 4. Okay, if I plug that in, let's put a 3 pi over 4 in there. It's going to be negative, so that gives me the 3 radical 2 over 2. Ooh, negative though, right, class? All over. If I plug it in there, I'm going to get radical 2 over 2, but it's already negative, so I'm going to get negative root of 2. 2, what? Oh yeah, 4 over 2, so it'd be negative 2 radical 2. Spling, spling. The both 2's are on the bottom. I get a little Triforce, right? You take that bad boy, put it in there. Booyah, dunzo! That is how I always get these things. Somebody in class teach me how to get these things off of here. They keep on coming up, okay? So we get 3/4. We plug that in. Booyah, that problem is donezo. All right, let's keep bringing on the calculators. All right, this video is probably getting long, so I'm going to try to rally. All right, without a calculator, find the horizontal and vertical tangency. Right, we've been doing this stuff all year. How do I find the horizontal tangents? Well, it's just dy over dx, right? And horizontal tangent is whenever the derivative is 0. Vertical tangent is whenever the derivative is dne, a 0 in the bottom, right? So let's go ahead and find the derivative first, which would be dy dt over dx dt. which would be equal to, okay, let's see, dy dt. That's just a little 2t minus 3. Okay, dx dt is a little 2t plus 1. All right, so horizontal tangent. Horizontal tangent would be whenever the derivative is 0. And the derivative is 0 is whenever the top is equal to 0. So at 3/2. Okay? And then believe it or not, all you have to do is, it does say to find the points. Okay? So at 3/2, all you have to do is here is put your x and your y. And your x is going to be 3/2 squared plus 3/2, right? You go ahead and do this math on your own, class. And then the y is going to be 3/2 squared minus 3 times 3/2 plus 5. Okay, do that work on your own. Put that answer in your notes. Vertical tangent. Vertical tangent is going to be whenever my derivative's denominator is 0, which gave me a dne. And that would just be there, which would be when t equals -1/2. And then how do I find those points? Well, those points, all I have to do is plug that stuff back in, right, class? I'm going to plug that stuff back in.